Right, cheers guys. Thanks for having me. I'm here today to talk about the stuff I've been doing with interactive AR. Over summer I worked with Andreas and Adrian, and you've probably seen it working on the AR spider. And carrying on from that, this semester I've been working on more general interaction with the gesture library that we're trying to work on with Sam and Adrian and a few others. Both projects use that setup on the right. Got the connect positioned above your head, and you interact in that tabletop space. I'm going to go into what I've done in a bit of detail, so apologies in advance for those of you who don't have a computer science background. Dan's previously talked about the architecture of our gesture library, so this is what we're trying to get up and going. There's 5 modules there. The modules I've been working on mostly are tracking and modelling. Tracking is really important for interactive AR because by knowing the motion of real-world objects, we can accurately model how they interact with virtual objects. And obviously modelling is important because we have to have some sort of model in the computer to decide how these objects interact with the virtual content. So my aim this semester was to develop a framework to allow realistic interaction in AR scenes with arbitrary objects. The reason I say arbitrary objects is because a lot of people have done stuff where you've got to mark your object's got to wear a special glove or something. I wanted to try and do it with any object. I'm going to talk a bit about different ways that people have enabled real-world objects to interact in AR scenes. There's 3 main methods: marker-based, model-based, and appearance-based. The main difference between these methods is how they turn observations into computer models of the real world. Marker-based interactive AR is the simplest method, where you attach a machine-readable marker to objects that you want to have interactions with. This work on the left here is done by researchers in Singapore. They've attached a marker to this, that's a Lego forklift up there, and the computer tracks that marker. Inside the computer they've got a model of a basic physics model of the forklift, and you can interact with virtual crates and stuff with that internal model. This form of interaction is not that satisfactory because it's not very natural. Everything that you interact with has to have a marker on it for a start, and this also means that the scope of interactions is really limited. You can only really interact with things with markers on it, and everything has to have a model matching it in the computer. Because we're trying to work with arbitrary objects, we don't want to have this additional setup and this predefined knowledge. Now, model-based interactive AR is quite a bit more complex. It fits predefined models to observations of the scene. So no markers are required because typically a depth camera is used, and you try and match. This example here is a Greek university or Greek researchers, and they tried to match what they saw in a Kinect with a hand model. You can get some pretty impressive interaction. These guys did really well. But again, you need that predefined knowledge, and so it's not quite ideal for us. THAM's using a similar model-based approach to enable gesture-based interaction, but that's higher up the gesture library, and that's not what I was working on. The type of interaction, the type of approach I use is called appearance-based. It requires no predefined models. It builds models based entirely on what it sees. So Adrian and Tham last year worked on AR micro machines, and so what it did is use the Kinect to map out the environment that the cars drove around. And so no predefined knowledge was required. You could put pieces of paper there and drive up them. You could use your hand. You could use anything. So that's the approach I took. And the state of the art in interactive AR at the moment is Kinect Fusion. I'm sure some of you have heard of it. What they do here is a Kinect is sort of waved around the room, and it's tracked, and a high detail 3D reconstruction is generated of the environment as you wave the Kinect around. This approach, the tracking and reconstruction at the same time, is what inspired my solution. And Kinect Fusion also allowed you to interact with thousands of particles there, interacting with the real world, but it assumed the scene was static, so dynamic interaction wasn't very easy. The motivation behind what I'm trying to improve comes from 2 areas. In AR micro machines, there was no dynamic interaction. There's no tracking of anything. So, for example, that person's holding the car in his hand. If he moved his hand sideways, the car would fall down because we don't know how the hand's moving, and we couldn't model friction or anything like that. So I tried to improve that, and also, this is going to come up. In PhoBAR, we tracked objects in 2D, which works fine, but as soon as we start moving in a third dimension, the tracking fails. Okay, so as soon as we flip our hand over, because it's only tracking in 2D, the spider doesn't appear on the bottom of your hand, it just kind of shifts around and the illusion's broken, basically. So to get better interaction, we need better tracking, and we need tracking in 3D. The other issue with a lot of AR programs is occlusion. So how do we know whether an AR object should be visible or hidden behind some real object? The Kinect makes it a lot easier because with the Kinect we can model the environment, so we can get an idea of where objects are and whether they should be hiding augmented reality content. AR micro machines assumed everything looked like the image on the right, so it assumed that every object the Kinect saw went all the way down to the ground, which is great because in AR micro machines it's mostly just books and various things on the table. There's not a lot of interaction happening under objects. Whereas for PhoBAR, it's more like the situation on the left, where your hand might be above the table and the spider might be underneath, and situations like that. What to notice between these two scenarios is that they both look exactly the same to the Kinect. Right, there's no way of differentiating whether in this one we shouldn't be able to see the object, in this one we should. Okay, so we need a better model of the real-world objects in the scene to get better occlusion. So my solution to these problems was to do tracking and modelling in a sort of circular motion, to use one to inform the other. So initially, the tracking module receives a new observation from the Kinect. The pose of the object in this observation is found relative to the model. And that way we can align the new observation with the model. Then we pass it to the modelling stage, which updates the model based on this new observation. The modelling stage then passes this new model back to tracking, and the process repeats. I use Point Cloud Library, or PCL, for the 3D data manipulation. It's quite a new project, and I'm sure it'll get better in the next year, but if anyone else is working on it and they want to ask me things, I've managed to work out a few of its sort of funny little things that it does in the last few weeks. So this is how my application is, the basic framework of my application. I begin by segmenting out the foreground. In the gesture library, this is a whole module on its own, and we haven't really, we've got a few different ways of doing it, but we haven't really looked into it in depth. So I just built my own quick, basic segmentation algorithm. But the aim is that any different one could be substituted in when we do design a better one. So the focus was steps 2 and 3, tracking and modeling, and that can be used in any. Well, that's going to be part of the gesture library. Can be used in any application. And the last stages 4 and 5 were a particular demo application I made to show what's possible. I made a simple program where you can interact with you could use real objects to interact with a virtual tennis ball. So I modelled the real objects with physics proxies, which are little spheres that follow the shape of the hand or whatever you're using to interact, and we use it in the physics engine to enable interaction. I'm going to discuss each of these stages in a bit more detail. So the first one's foreground segmentation, and as I say, this wasn't a focus of mine, but I did it anyway. We're using the Kinect, so we can easily use a depth threshold to segment out just foreground objects. What I did was at every pixel on the screen, I recorded the deepest value that I'd ever seen, and that was I decided that was the table. And if an object was at least 98%, the depth was 98% or less, then it became part of the foreground. And then I just did blob detection to group objects together. Now the main part of my work, and it's been a lot of time fiddling with parameters and stuff, is tracking. I use the iterative closest point algorithm, called ICP, to do the tracking. And this is what they used in Kinect Fusion, and so that's why I decided to use it. How it works is that you have 2 point clouds, okay, like those two there. And one's we're going to call the model, and one we're calling the observation. We're trying to find a rotation and a translation of the model to match it to the observation. So what we do for every point in the model, we find a corresponding point in the observation. And then we find a transformation that makes the distance between corresponding points as small as possible. Then we repeat. We find a new set of correspondences, and a new transformation. And eventually, we converge to some solution. However, it's not that simple, because there are a lot of different ways ICP can fail, can get stuck in local optima, and we've got to decide how we're going to find the correspondences and in what distance are we going to minimize. First of all, how we find the correspondences. The simplest way and the most obvious way is to find the nearest neighbor. So for every point in the model, find the nearest point in the observation. That's great, except it takes a long time to search. Right? Finding nearest neighbors is computationally intensive, so we want to look for a better solution. Now, a lot of people, or the literatures on real-time ICP suggests we use projective matches, which is when, if that's the viewpoint, you take the model point and project it along the viewpoint line to find the point in the observation. And that's the 2 points you correspond. This is really easy because you can do it in constant time. Okay, it's just a lookup. However, I found that it produced matches which caused ICP to underestimate the motion of objects. So it would consistently not think my object had rotated or translated as much as it actually had. So I used a new approach, which I haven't seen used elsewhere, which I called randomized projective match. So instead of just taking the projective point B, I randomly selected a point nearby, one of those points C. And what this does is it means that although any one point might be a bit out, on aggregate, we get a better result, or I saw that we got a better result than projective matches, but it still runs in constant time like projective matches. And in terms of metrics to minimize, there's really two options. There's the point-to-point distance, which is obviously the distance between the 2 points. There's also another solution that people have come up with, which is called the point-to-plane distance. And what that does is it finds the distance from the model point to the tangent plane of the observation, of the point. To the tangent plane at the point of the observation. So it's that distance B. You might wonder why this is useful. Research has shown that it makes it converge a lot faster. However, it does mean that we need normals, and I found that PCL couldn't estimate normals fast enough to make this viable. It's the better solution, but we couldn't get it running in real time. Also, the point-to-plane distance metric's unstable if objects are approximately planar. If you've got a Kinect looking down and you've got your hand at any sort of orientation, it looks more or less like a plane. And so therefore, you can sometimes get instability where the ICP just gets the complete wrong solution. The third consideration was avoiding local optima, which is when ICP converges, but it doesn't converge to the best solution. And the real problem I had was that whenever, if the Kinect's looking down, whenever the object moves in the plane parallel to the table, it's very hard for ICP to converge well. If you look at this picture here, if that shifts slightly to the right, almost all point matches are really equal. They're almost all at the same point. And so ICP doesn't move, and we underestimate the translation. I solved this by applying an initial guess of the object's transformation. So what I did is in the segmentation step, I found the centroid of the blob that we were looking at and found its motion. And I used that motion to bias ICP to begin with, which improved, didn't eliminate this problem, but certainly improved it. And there's a lot of scope for finding better ways of biasing ICP to get better solutions. All right, with the tracking accomplished, the next step's updating the model, the internal model of the objects. So what we did is we've used ICP to align the observation in the model, and then we update the model. So we add observed points that aren't in the model, and we remove points that don't agree with the observation. Now this means that if you're using your hand's open, then you close your hand, eventually the points that were your fingers disappear, so we allow some non-rigid deformation. If too much of the object deforms non-rigidly, then ICP will break, but we do allow some non-rigid deformation. Now the aim was to try and build up a model as the Kinect saw lots of different views of the hand. This really depends on how good your tracking is. And my tracking was on the way, but it wasn't good enough to get a sort of a closed model. I'll talk more about that later. All right, the application I made was a just simple little demo where you could play with augmented reality tennis balls, interact with them with your hands or pieces of paper. And how I achieved the interaction was to represent the models that I'd already built in the modeling stage, represent them with spheres in the physics engine. So you can see I just attach spheres to all the model points, or a collection of the model points, and plug those into the bullet physics engine, which did the simulations for me. And then finally the AR scene was rendered. I used only one perspective, so I only used the Kinect looking down, just for simplicity, because that wasn't really what I was focusing on at this point. Using the Kinect looking straight down did allow me to get occlusion perfectly, because at every point we can see is the hand or is the object above or below the AR content. So you can see on the left there, you can cover the balls up and stuff like that. We're yet to try to use the models to do occlusion from a different perspective, but that'll be interesting to see how it goes. I didn't include shadows, but they would have been great to get a bit of more idea of where the ball was in the scene. And Tham and Adrian did include shadows, so the framework's there. I just didn't implement it. The tracking and modeling that I did ran at sort of 25, 30 frames, which is good, which is real time. Unfortunately, once you bring in the physics simulation and all that, it got down to 12 frames. It was only on a single core, and most of the algorithms I use are parallelizable. So whether we use the GPU or a multi-core system, there's definitely scope for speeding things up. This gives you a rough idea of what the application does. Obviously, it runs even slower when it's drawing hundreds of spheres, but you can see you can use anything. You can use a piece of paper, even though the piece of paper's got no sort of texture on it, which might stump other systems. There's really a huge amount of sort of tightening up that could be done, but you get the idea. I didn't spend too much time on the actual application. It's more on the framework behind it. All right, so to evaluate my tracking algorithm, I used a synthesized scene, and the reason for that was because it's very hard to tell exactly how a real object is moving to compare it to what my tracker says it is doing. So I synthesized a scene. There's a model there, if you can see it vaguely. It's called the Stanford bunny. It's just a bunny rabbit model. And I created an artificial scene with a flat background and the bunny on top of it. I added some noise to simulate data from the Kinect, and I ran it through my tracking algorithm. I moved the bunny in a known way, so I knew how fast it was moving, I knew how it was rotating, I knew how it was moving, and I compared it to the output of my tracking thing. I wanted to find out how much drift my tracking had. And now drift, if you don't know, is the measure of how much error accumulates over time. So a 10% drift means that for every 10 centimeters something moves, the error is out by a centimeter. Okay? So my algorithm had a translational drift of 4.3% and rotational of 8.5, which isn't bad, but it doesn't mean that if you rotate an object 360 degrees, you've lost a good 30-odd degrees there's a good 30 odd degrees of error there, so the models don't close up. As I say, the better we improve the tracking, the better modeling becomes. So the improvements that I managed to achieve, we can now got 6 degree of freedom tracking, so tracking in 3D, which is great because we can allow all sorts of new interactions. We have not yet tried it, but the models we've built up will allow occlusion to be solved in a better way. And we don't need any extra hardware. All we need is to connect. Don't need any markers, don't need anything like that. So it should make for quite a good, cheap setup for various different applications. The limitations of what I've done, the demo only runs at 12 frames a second, as I said, but parallelization is possible. The tracking does drift, and there's so many parameters to optimize. I'm going to talk to a few people who are more interested in this afterwards, but there's so many. Every day I sit down and I tweak something, and tracking gets a bit better. So there's so many different things to optimize that it's going to take a while to get it really tight. The other thing is that high level interaction is not possible. For example, you can pick up a ball or whatever, but you can't pick it up by that or pick it up with any kind of grasping gesture. That's going to be more Tham's work when he implements the gesture-based interaction stuff. So stuff to be done in the future. Basically, the tracking is the real thing that needs work, and there will always be work to do. ICP may not be the best. I used it because other people had. There might be better solutions that use, for example, the color image as well. This works on nothing but depth. Or it could be maybe a combination of a few different options. For example, you could use optical flow to bias the ICP search so that it converges to a better solution faster. PCL also contains feature descriptors, which work on both RGB and depth, which can be tracked instead of using ICP. That might be quite good for tracking objects if they get covered by other objects. Another solution is using particle filters, which would allow multiple tracking hypotheses to be tested. But it would slow down the system quite a bit. There'd have to be some optimizations there before you could test that many hypotheses. The next step is probably to improve occlusion. What we'd do is we've got this model, we've got this point cloud model of every object. So we'd find, if we're using a second perspective, connects here, we're using a second perspective, we'd find the hull of all the points in that model from the second perspective and use that to occlude the virtual content. And as I say again, performance improvements are definitely possible. I didn't focus on it too much here. We can use multi-core or GPU parallelization to speed things up. Not really my area of expertise, so I didn't work on that. All right, thanks very much for having me. I'm pretty much at the end of my time here at the HIT Lab, so I'd just like to thank you all. Had a great time since I've started here in November. So cheers. Really like to thank Andreas and Tham and Adrian, who's away at the moment, for helping me out and giving me some exciting projects to work on. I'm planning to go to the States to do a PhD next year, but until then I'll be around in and out of the lab, especially if you've got free lunches. I might come back for that. Cheers. Nice.